Hey everyone, it's Avery again. This is the second video. This video is really optional. Hopefully you can just look at the starter code and figure things out on your own, but I know the starter code is a little intimidating. So I'm going to make a video that just goes through the starter code, and then hopefully that will help you navigate this, rather chunky code base a little easier. So hopefully you watched my previous video. You should have a good idea of all the different layers you need to implement. I have the project spec over here as well, but don't forget, you are supposed to go into the section notes, and you are supposed to go over section 7 and section 8. Right, section 7 contains the that's not supposed to happen. Incognito mode. Okay, there we go. Section 7. Okay, so section 7, you should be able to see problem 2 is the most useful. Yeah, so problem 2 is the problem on direct, singly indirect, and doubly indirect files. This will help you a lot when you do the math for the inode index lookup functions, because for that you'll need to determine, given a block number, does it go in the singly indirect one? If so, which one? Or does it go in doubly indirect one? Okay, so all the math there, you can learn that math by doing problem 2. Section 8 has this really nice slide deck. Go to the slide deck. And this slide deck contains all like the information you want. So a lot of the things I went over in the video, a lot of diagrams are in this slide deck. Okay, it's a very comprehensive. I stole some of the diagrams that I drew in the last video from here. So highly recommend that you just go through these slides so you can understand everything you need to know. Okay, you should imagine that this is more like what would be covered in a lecture if you were to go through the assignment, while what I wrote was just like a quick summary of that. Okay, so if you need a reference material, check these out. All right. Okay, so in the starter code, once again, you all know the drill. You know how to clone the starter code. You also should do this thing. This thing, if you remember what the first part does, this creates a soft link to the test disks. We don't want to make multiple copies of the test disks because they're pretty big. So you all have a soft link to it. You don't really have to worry about what this does, but just, in case an exam comes up, just know that this thing creates a soft link, and you can review what a soft link is and what it does. How it's different from a hard link. We talked about the structure of the code. To test the code, same thing. The make, there's no .test option that was available in the previous ones. It's a little annoying for me because those are really helpful. But here, you can run an individual test by writing this thing. The options, there's two options, -i or -p. -i tests the first 2 layers, -p tests the other 2 layers. Okay, so you sort of have to implement half the project to be able to test anything, and you have to fully implement everything to test the rest. The test disks are given to you here: basic, def file, and dir frame size. I believe basic gives you like a very small file, so even if you don't have singly and doubly indirect lists implemented, I think you should be able to pass basic. Def file requires you to support big file sizes, and then dir fname size, I believe, is testing your if you have file names that are very large. That's my guess. You can also type -- run tests. I don't recommend you run this until the very end when you are just double checking, making sure everything's fine, because this prints out a lot of stuff and it's hard to parse it because it prints an inode for every single file, and dev file has a lot of inodes. I sort of went over this, just implement it in the order from bottom up. Okay, so the inode, the imode here, let's talk about imode. So imode is, there's a 16-bit integer, so it's 2 bytes. It's not really not really like a number, it's more like a bitmap. It has a lot of individual bits, and it tells you the different properties of the inode. Okay, and then there's some information. You can actually go to inode.h. Let's go to inode.h. So inode.h actually contains, you can see here the contents of inode. We'll talk about this part We'll talk about this part actually a bit later. But yeah, the I mode contains just a bit vector of like a lot of different information. And here is all the different things you might need. So you can check if something is a directory, if dir, check if something is a I large is going to be important, right? If you're using a small addressing scheme using direct pointers, or a large one using singly and doubly indirect, you use this I large. And then the way you use it is you simply do this thing where you bitwise or it, you bitwise and it with something to check if it's true or false, 1 or 0. Yeah, so that is this part. Yeah, you can read it to get more information. I believe the most important one is the I large one. Typecasting. Yeah, so I mentioned this multiple times throughout the video, but yeah, avoid declaring generic buffers unless you don't know like what the contents are. If you do know what the contents are, for example, like in inode iget, if you do know that the contents are structs, inode structs, then you should declare your buffer to be an array of inode structs. Okay, if you know the type, name the type. Don't just give it a generic name. Furthermore, there's a lot of like CS107 stuff that you might be tempted to use, like memset and a lot of the memory functions. Whenever possible, just directly assign, use the equal sign. Okay, yeah, that was taught in CS107. Also did that here. Cool. And then miscellaneous tips. I went over most of these. Okay, I think most of these is just easier to just go over in the starter code. So let's go over to the starter code. In the starter code, you can see that the first file you have to implement is called, oh, let's go to the block, the disk image first. So disk image here, you can see that in disk image.h, you can see the function you will use is disk image read sector, which takes in a file descriptor, a sector number, and a buffer. Okay, this file descriptor you can get using the Unix file system.h. Unix file system.h contains a lot of constants. Right, these constants tell you like where the root inode is and where the inode start sector is. It's going to be super useful when you implement the inode.h. Yeah, so these are constants. Definitely use these. This struct is declaring what the file system is. You don't really need to care about the super block. The most important thing to care about is this DFD. This is the file descriptor you need to use to call the disk image read sector function. Okay, so that is here. The inode.h. There's 3 functions. You only have to implement 2 of them, the first 2. This first function is basically answering the question, give me the contents of inode number 12 and put it in INP. So you have this Unix file system that's passed in as fs. Using fs, you can get the file descriptor that you need to call the disk image read sector function. This I number is the inode number that I've been referring to. And usually this last parameter, if it's a pointer, it's almost always a output pointer. So it's, you put the contents of the output. So here you're giving the contents of the inode itself. You would just copy it into this space. Okay, now you have this function called inode index lookup, which takes in a struct Unix file system, fs, it takes in the inode. So pointer to the inode is pretty much always going to be the same inode that you had output previously. And then you also have this block num. I personally would prefer that you rename this as file block index. And just to avoid confusion, this is like the, the 4th block of an inode or the 100th block of the inode. Okay, yeah, don't call it block num, because block num, there's another meaning for block num, and that is when you do the singly indirect, like each of those numbers within the sector, those are direct block numbers. So just prefer not mess you up. Rename this to file block index. And you can rename that in your inode.c as well. Yeah, rename this to block index. Okay, so that's the inode. In the inode function, you will definitely need to use the constants in here, the Unix file system. And you should also look at inode.h. This contains the actual structure of the inode. We talked about the mode already. When you do the small file and big file, small files, this I_8 gives you 8 direct block numbers. Yeah, remember that block number is here. Yeah, let's not overuse terminology. This is what we call a block number. It's they're really sector numbers. Those numbers tell you that the 0th block or the first block or the second block, which the contents of those blocks are in which sectors. But if you're using a large file scheme, which you can determine in the I mode, and using the I large here, if it's in the large mode, then the first 7 are singly indirect numbers, and the last one is a doubly indirect number. Okay, so this I adder is going to be important. If you added up the size of this inode, it would be 2, 3, 4, 5, 6, 7, 8, and then 8 plus 16, that is 24. 25, 26, 27, 28, 29, 30, 31, 32. So the size of this inode is 32 bytes. So in inode.c here, disk image size is 512. Struct size of an inode is 32. So you can know that there are 16 inodes per block. Here, okay, this constant is confusing. Nums per block. That's a confusing constant. You can rename it if you want. This constant basically means how many block numbers, like the block numbers are the like direct block numbers or singly direct doubly block numbers. Those are the numbers, those are really sector numbers. These, you can calculate how many there are. Each block number is 2 bytes. These are small block numbers. So there's 512 bytes total in a sector. So each sector can contain 256 block numbers. Okay, use these constants. We declare them for you because they're important. And probably they got frustrated that students last year didn't declare them. By the way, all the numbers that I used in the examples in the iPad, you should not use magic numbers. You should always use these constants, whether these constants or the constants in the Unix file system file, or you declare your own constants. Okay, so that's the inode. Let's go to file.h. Okay, yeah, once again, let's rename this block number to file block index, just so we don't confuse what a block number is. Yeah, the file get block, it takes in the inode, the I number, I mean, and it takes in the file index, like you want the 4th block, and then it puts the output as, this is just an output buffer. The int here should return the number of bytes, which is usually, it will be the same as the sector size, 512, except for the last block's size, the last block. File.h, also don't forget to rename this just so it's less confusing. Oops. Okay, that's the file. Once you're done with that, you can make the project, make clean, and then you can test the project using /test, disk image access -i to test the inode layer only, and then you can run test disks disk image oops, I am in the wrong project. I'm still hung up on project 6. There we go. Okay, you can check the answers. If they differ, you can go to test results, which you can check what the correct test results is. This is, I found, has been really helpful because you can check if there's something that doesn't match, you can check which ones don't match. Okay, you can see if it's the big files or if it's the really tiny files to try to debug. Debugging is really hard on this project because a lot of it is math. If you just make a mistake, it's hard to debug that. Okay, in the directory layer, nothing interesting here. We went over this in the last video, but there is this direct entry v6 here, and then this is just like each row in that table I drew. There's a 2-byte inode number, and there's a 14-byte C string basically. This C string might not be null terminated, so use stir and compare, not stir compare. All right, that's it for this file. Let's look at the last file, which is the path name file. And then path name is very simple. You just give it a path name. And in your .c file, you have to use, you can see here that we've already imported the string.h function. So you can use all of the string functions, stir, len, stir, compare, stir, sep. Yeah, do all that code inside here. Okay, I think that's it, mostly it for what I need to go over. Yeah, the last thing is just this checksum. You don't really have to worry about this checksum file. It's just to test the correctness of your output. It's pretty much impossible to debug just looking at a checksum. So all you know is something is wrong, and you have to look at the test results to see which inodes look wrong. Okay, once again, try to try to get yourself unstuck. Print if you are not sure why something is failing. Before you ask for help, print out everything that you calculate. Like for example, the doubly indirect or the singly indirect. Print out every variable, work it out on paper, and double check if everything is correct. If something is wrong, then you can then look to see what went wrong. Okay, remember, try to unblock yourself before you ask for help, either on ed or at office hours. Okay, this is just a good skill to learn. We're nearing the end of the class. Hopefully you learned a lot of debugging skills through this class. All right, otherwise, thanks for watching the video. Hope this was helpful, and good luck with the project. Bye.